Hello, thank you everybody for coming to our session. I'm Andrea Barisani, this is my colleague Daniele Bianco, and we're going to talk about our open source project called the USB Armory. So we have a company which is called InversePath. We presented a few times at Black Hat. Our first talk was just to give you a little bit of background about what we do about injecting traffic navigation messages into cars. Then we've done in 2009 a talk about sniffing keystrokes from power outlets. In 2011, we presented a talk about credit cards. And 2 years ago, we did a talk about packet-in Ethernet. So this just to show you that we're heavily involved not only in software security, but also hardware security. And we like to tackle kind of peculiar topics concerning hardware. So, and every 2 years, we try to do a talk and a research. And this year, we decided to build something from a change rather than, picking things apart. And then the idea for the USB Armory project came out. So what is the USB Armory? So the USB Armory is an open source compact device which basically implements a secure computer that you can carry around. It was designed for personal security applications. And the first idea that we had, the reason why we had the idea of building such a device, is that we wanted something that we can carry around with us in our pocket that could be as much trusted as we could possibly make it, and it would allow us to have encrypted storage. There are a lot of USB flash drives that they claim they provide military-grade encryption or whatever certified encryption, and you have no idea about what's going on either in the hardware of the device or in the firmware and in the encryption which is actually implemented. And this class of devices has been known to have very poor quality and implementations that are not secure at all. So our first idea was to have, first of all, enhanced mass storage. So something where if I would just copy a file on a device, it would be, optionally scanned maybe for malware or whatever, but encrypted with something that we know, whether it's, GPG or other means, and then put on storage in a way that we would control it. So we thought of a device that would just emulate a mass storage, which is the protocol that is normally used for your USB drives, but that would allow us to be in control of the encryption process that's going on. And we wanted the encryption process to happen on the device itself. That was one of our goals. And then we thought, but if we have something which is not single purpose, but has a little more of horsepower and that can do, execute more custom code, then we can also have something that rather than exposing a mass storage device, we could just expose whatever web application that we want and have a convenient interface for just uploading files and then downloading them again and then maybe sharing them in a secure way. That was the goal, to have something that we can easily use for file encryption and secure file sharing. And pretty quickly, the requirements for such a device went from having some dedicated single-purpose hardware to try and have something which is a little more generic and which became to get the shape of a standard open source computer in such a tiny form factor. And then we thought, if we have this kind of custom functionality, then we could do all kind of cool features, such as, we can have fail-safe actions where if I do a specific action, then we have data self-destruction, for instance. So if I type a specific password, if I copy a certain file, so if I not do a certain action that I'm supposed to do, then everything gets wiped or locked. So things that right now with single-purpose USB devices meant for security, for secure storage of files are simply features that are not there and not possible to do. And then we thought, but if we have a standard computer on such a compact form factor, then we could do other things. We could use it as an SSH proxy. I go to computer which I don't trust particularly, I can log in into my device with a throwaway password, and then I can SSH out with my keys, which are stored on the device, and then to my servers or whatever. That's one other application. We can have a password manager. If we have a device which I can easily connect and can expose web applications that I can control, then you can have all kind of functionality, such as, yeah, a password manager. Or authentication token of, whatever kind that you want to. And also, one of the other interesting things that was thought of while developing this, we can also have the USB device, since we have something which is actually a full active computer and no longer a passive device, we could have the USB device authenticating the host. So you can have it so that when you plug your device on a computer, the device itself will try to probe your host and understand if it's trusted or not, and then take whatever action depending of how you configure the device. And also other applications, you can have a Tor router on it if you have a network computer connected in such a small form factor. You can have a Bitcoin wallet and a VPN and so on. So all of these ideas started, flowing once we thought to have a generic computer on such a compact USB device. And so right from the beginning, we set a few design goals. So it must be a USB power, of course, so not requiring external power supply, because that would be clunky and inconvenient. It must be very small. It must be a little bit of future-proof, so have a fast CPU and a generous amount of RAM. We work a lot with embedded systems on a daily basis, either breaking them or analyzing them. And most environments are very, for cost saving, are very constrained in the amount of resources that they give to you. And this, of course, if you are developing one single purpose task for this device, it is fine. It's good engineering. But if you want something which is a little bit more generic and that we want to propose as a platform for other people, that we want it to be fast and with good specifications. We must have secure boot, of course. We must be able to boot code that is signed with your keys, not our keys as manufacturer, of course. So not the kind of secure boot that you have on your normal laptop where you can also reset it if you want, but something that can permanently fuse signing keys, and then only your code can be booted off of a specific device. Must provide standard, convenient connectivity over USB. And very important, the developing and execution environment must be familiar. We didn't want to have really customized and compact Linux distributions or development environment. It must be easy to develop on this device. And the design must be open, being a security device with the goal of handling very sensitive data. The hardware and, of course, the software must be as open as it can get. So when developing this hardware, the first and most important phase is selecting the right components for developing the hardware. And the component that we selected for the first version of this device is the Freescale IMX53. It's an ARM Cortex A8, which can be clocked between 800 and 1 megahertz and 1.2 gigahertz. So really fast for a USB device, if you think of it, of this size. I mean, we're talking about something which is very, very tiny. Almost all datasheets and manual are public, and there's no NDA required for features such as secure boot or things that we really care about for security reasons. The datasheets are okay. They're not, when you look at datasheets for components, there's always some quirks and some issues in comprehending them, but the Freescale, I would say, are okay, far better than other vendors, so that was eased the development process. And we also have a good implementation of ARM Trust on this device, and secure boot, secure storage, and secure RAM for cryptographic purposes. There's a detailed power consumption guide available, which was very important for us to ensure that the device can be powered from a USB port. And there's excellent native support for Android, Debian, Ubuntu, FreeBSD for this processor. So that met our goal of providing a familiar development environment. And there's good stock and production support guarantee. You don't want to commit to a design and then Freescale tells you, sorry, that part is not available anymore, because that sucks. So that's also an important part of the development process. The system on a chip that you use has a lot of features that we are not using because we are making a USB device. We're not connecting it to display, to GPS, to SATA disk, and so on. So it's a fairly complex processor, and we power on only the things that we need. So concerning Trust Zone, so you might have heard of what Trust Zone provides. So Trust Zone is instruction set support for certain ARM processors, which allows you to have execution domain separation between what is called to be the non-secure world and the secure world. And one of the long-term ideas for this platform is to leverage on this kind of a feature for providing more separation between the OS that runs on the device and the more sensitive code that can maybe handle cryptographic keys and so on. And the idea is that you have your own user mode applications and privileged kernel applications, so your Linux environment running in non-secure world. And then whenever you want to do some operations which somehow must be executed on a more privileged context, you can ask to switch to monitor mode, and then the code which is in the secure domain gets executed. And this code has its own user mode application, its own privileged kernel, and more importantly, it can also have its own device driver for specific hardware subcomponents of the device. And these hardware subcomponents can be only assigned to the secure domain. So for instance, you can decide to assign the micro SD controller only to the secure domain, and the non-secure domain would never know of the existence of the micro SD controller. So by hardware, it is physically, its access is physically blocked. And so by defining an API between the non-secure and the secure world, you can have a separation which allows to expose the minimum surface to the non-secure world and control exactly what you're doing. One of the applications is, for instance, that you might want to handle encryption and decryption of the micro SD card completely into the secure domain. And the secure domain holds your passphrase, which you input at boot time, for instance. And that's held in the secure context. So a non-secure domain, if it's compromised, for whatever reason, cannot physically go in memory and see the passphrase that is being held into the secure domain, because the context, the execution context and the memory are completely separated. And at the same time, the non-secure domain cannot access the micro SD card directly. So this is just one example. And this is also one of the reasons of why we have chosen this specific system on a chip, because we know it has a good support for Trust Zone. And the hardware that can be assigned, depending on the specific system on a chip, you might be able to have different kind of granularity in what you can assign to either the two domains. And with this specific system on a chip, it's very flexible. You can assign the USB controller, the micro SD, the serial port, or the LED, for instance, GPIO. So on the board, we have one LED that we can decide to assign to secure domain. So if the LED is turned on, you know by hardware that in that moment, the secure code is being executed, because the non-secure code has no hardware means to access and turn on that LED. And if the non-secure domain tries to access a device that is not supposed to, you can have an exception which then can be trapped. So the idea is to have a rich OS into the non-secure domain, such as Linux, and then more compact, more tiny, maybe a microkernel or directly our assembly code running into the secure world, handling a very specific operation that you might want to confine to a different execution context. So the hardware, Darth Vader is our official mascot because we think it's cool and matches the color of the board very well. So the hardware is completely open source. The software is completely open source, and this is the final version of the device. Also, after the talk, if you want to come and see it, we have two samples here that you can come and take a look so that you have an idea of the dimensions of the device. The final specifications, so we put the IMX53 on it. It's USB horsepower. The power budget is absolutely fine. It's very tiny. We have a 5-pin breakout header where we can break out GPIOs and serial console for debugging capabilities or for other purposes, like there are people adding buttons on the pin header, which is here, so that they can emulate kind of YubiKey style functionality where you press the button and then you trigger a specific action. We have the LED, which we can trigger on, we can assign to trust on the secure domain if we want to, for a secure mode detection, so that you make sure that the normal world is not phishing for your password. And we have excellent native support. So now we have Ubuntu, Debian, Arch Linux, we have Kali Linux, we have the Arch Assault modules for Arch Linux, which provide also penetration testing tools which can be easily installed on it, just like you would do on a Raspberry Pi or other bigger ARM devices. Also good for penetration testing, we could do USB device emulation. So we emulate CDC Ethernet as default, so it just shows up as a server which you can connect to. We can emulate also mass storage, keyboard, and so on. So we also use it for low-level penetration testing of USB devices, because with the Linux USB gadget framework, we can control and emulate everything which is exposed on the USB side. So it's also good for those kind of offensive capabilities. It's probably, you can consider this as the perfect mean of implementing bad USB if you want, because this device can be whatever you want and it's active. It can run your firmware, and as soon as it's plugged in, it can execute, whatever you like. And it's completely open hardware and open software. Now, interesting thing that we realized after developing the hardware is that not only we can run in device mode, which is our default mode of operation, but we can also run in host mode. So you see here the USB Armory attached to, so this was one of the first iterations. Now we have an adapter for that, but we can plug it directly to a keyboard, a mouse, and a USB display, but just by inverting the role of the USB device. So from device, it becomes host. And you see it here. So here we use a MIMO display link USB monitor, browsing a completely random page on the internet for your benefit. So, and you have a USB power hub here on the right. So the hub provides power to the Armory itself, and then the Armory itself sees the hub, and all of the any USB device which is basically supported by Linux can be attached to it. So now we made a trivial adapter for this purpose, which basically what it does, it bridges from female to female, and then you can feed in power from a micro USB plug. So in this case, we provide power, we provide a Wi-Fi, USB Wi-Fi dongle, and here you have an access point where you can run Tor or whatever you want. And of course, if you attach your USB power hub, you can feed the power back in, and then you can attach more than one device. So it becomes, a completely standalone computer if you want to. And this is because the USB controller allows us a great freedom in configuring it. So even if we drive the USB ID pin to the ground, because we didn't think we could use host mode on the device, we can override that by writing to certain registers, and we can just ask the plug to be in host mode. So we just need to change the gender of the connection, and then you just have a standard USB host plug. So what were the challenges in developing this kind of hardware? So first of all, it is not some hardware that you can easily prototype on your own and soldering on your own, because there are two components which have a BGA form factor, which is called the ball grid array. So this is the SoC, the system on a chip, and down below there's the DDR, the RAM modules. You have 529 little tiny balls that are soldered to the board, and this is very difficult to do by hand. So this was one of the challenges. And we tried to be smart into developing this kind of board, and we said, let's make a breakout board where with a very expensive adapter, we can clamp the system on a chip without actually soldering it, so we don't risk losing the board and the system on a chip every time, and then we break out every single connection for debugging purposes. So this board works fine. It's great for accessing all the balls without risking errors in soldering and so on. So you just screw everything with a precision torque screwdriver, and it works. However, the issue was that enabling the power components, the tolerances were so high that hand soldering the power regulators, it wasn't sufficient for having a stable power supply to the device, which meant that we had to create a PCB for the power components. But if we create a PCB for the power components, then we might as well add the sock. And if we add the sock, then we might as well go ahead with the first prototype. So one of the lessons learned, and this, so the Darth Vader there, it's myself, and the Admiral, which is that is our colleague Andrea Rosano, which tried to do 7 iterations of this board, and at some point we went, you failed me for the last time. And we just decided to go with the first production because we weren't getting nowhere. And so this was an important lessons learned. So this board, which is very nice, turned out to be like a super Star Destroyer. So something very expensive, you know, big, which is completely useless and falls apart to the ground. But it's a cool thing to have in our office now. So lesson learned, just go for the first prototype. You know, when you're making hardware, there's a lot of paranoia in, you know, there are things that might not work, but, you know, it's not as bad as it seems. So always go for the first alpha version, and, you know, you'll get lucky. This is what was our what happened with us. The second challenge was that since we wanted the design to be open source, we also wanted the tool that we use for the design to be accessible, because even if we release the design, if the tool to open and modify the design costs 30,000 euros, that's not going to help a lot the open source community. So we decided to implement this using KiCad or KiCad, which is an open source design tool, which is fine for most purposes, but when you try to make high specification PCBs with manual routing of the RAM, then things gets really ugly really quick. So the issue here is that when you connect a RAM module to a system on a chip, all of those traces that you see there, they need to be exactly of the same length. And if you only have one direction to make the connection, that you cannot do the routing on the sides of the system on a chip, you don't have much room for that. It gets really complicated. And also at the time, KiCad was not offering any length trace matching capability. So all of the work for connecting those traces was a manual labor in making sure that they were, you know, exactly of the same length, and so that we would produce, you know, have more probability of having working prototypes. And this was the most critical and most difficult part in designing the board with open source software. But, you know, other than that, it was fine, and I think it's pretty amazing that in 3 months of time we completely open source tool implement something like this. I think it's we've come a long way. 5 years ago, this I think would have been kind of unthinkable. On the other hand, the 3D graphing capabilities of KiCad, which are useless, are very, very good. So you can see your board in 3D if you want before having it manufactured, which is you know, kind of neat. This is the alpha prototype that we received. It was a little bigger because we had JTAG exposed so that we could debug. If the board for some reason would have boot up, we could at least understand if the issue was with the RAM or if the issue was with the micro SD controller or some other components. Of course, if the issue was with powering up the board, then it gets more difficult to debug, but we had test points for that. So the first version was a custom alpha prototype with a little more test points than what are required in the production version. And you can attack a JTAG connector on it and then step into the code and so on. But it wasn't actually required because, again, we got kind of lucky. So the first alpha prototype worked right away, to our surprise. So this is kind of an inspiration to make open hardware. It works. And it's very interesting to see that the power of this tiny device is comparable to a Pentium 2, but we have everything standalone and packed in such a compact form factor. So from the alpha, we did some beta revisions where we thought there were going to be the final design, but what we tried to do, we tried to be less conservative in the design and eliminate a few components that, you know, even if you don't follow recommendations, they can be treated as optional, and this to lower the cost of the board as much as we can. We also reduced the number of layers from 8 to 6 to see if it will work or not, and so on. And then eventually we added the LED for secure mode detection, and then eventually we ended up with the Mark I design. So lessons learned from production. The first iteration had some tiny inductors that after 2 weeks would just fall off the board, so they were very fragile. So make sure that you test for that before making 2,000 boards, because otherwise it's gonna suck. If 2,000 boards, the component is gonna fall off after 3 weeks. So that was one lesson learned. And the second lesson learned was really interesting in the beta versions when we were plugging the board and we would see a 5 seconds delay in the boot up sequence. So now when you have 5 seconds delay, that's a very precise time, what you do, you go and search in all data sheets of all components for the words 5 seconds, because you need to understand why that's happening. And it turned out that the power regulator enforces a 5 seconds delay if an undervoltage is being detected. So the question was, why do we get an undervoltage detection? And the reason was that for doing the gold plating on the USB connector, the manufacturer added these traces that were not on our design, that were going outwards towards the plug for depositing the gold. But the problem is that by cutting then the board, they would create 4 little tiny conductive dots that would make a premature connection with the USB connectors. And then the connection would be lost for the space, for the transition between this little tiny contact here and the actual pad, and then you would have a connection back again with the power. So this would create the undervoltage connection. This was kind of very interesting problem because it took us a few days to figure out what was the issue, and it was introduced in our design. It's one case where it's something that the manufacturer thought it was completely safe to do, but at the end it wasn't. So in the final version, we had the gold deposit connection done here in a safe manner. So this was kind of an interesting issue that we had. And this is the final design. So we have the sock here in the center, we have the RAM, we have the pin header, and on the bottom we have the micro SD card slot, which provides the OS. There's no other persistent storage on the device except for a few fuses in the system on a chip for the signing keys. So there's no BIOS, there's nothing that can be flashed. Everything gets booted out from the micro SD card, which we think it's a good feature, it's a good property security-wise. And everything else is power related, and we have the smaller JTAG pins here for anybody that wants to access JTAG on the board. For trust and support, so we now have upstream support on Gnode OS. So Gnode OS is kind of an interesting OS framework that allows you to have minimal real-time operating system in the secure world, and then you can boot up other operating system in the non-secure world. So with Gnode OS, what we can do, we can compile a minimally patched version of Linux with just some few loading addresses redefined, and we can boot Linux in the normal world and Gnode OS in the secure world. And Gnode OS provides a platform where you can develop your own module and your own functionality that can then be executed into the secure world. And concerning Linux support, everything now, the little things that we require were pushed upstream. So the bootloader, the Linux kernel, everything is stock. There are no there are no patches or customizations required to run Linux on this board, which we think was important for us. And this is one example of how you can use Trustnode directly without even Gnode OS, without any support. So this is one assembly example of a secure mode monitor. So this is the code which runs at boot. So we have a modified version of U-boot which executes this code at start, and this is the example with the LED. So what we do, we assign the GPIO, which is dedicated, attached to the LED, to the secure domain. And by doing that, the non-secure domain cannot access that GPIO because there's a hardware firewall, so to speak, that prevents that access from taking place. We also set the internal RAM to secure so that we can execute our secure domain code into the secure RAM, which is on the system on a chip. Otherwise, we would have to split the areas in the external memory module, which you can do. So you can have areas which are secure and areas which are non-secure. And then we have a secure monitor code, which here it's a very trivial example. So what it does, it checks if in the R0 register we put the X cafe value. And if we do that, then we jump to our secure monitor code handler. Otherwise, we go back to non-secure world. And this kind of switching can happen on demand. So the non-secure world can raise an exception and ask the secure world, please do something for me. And the API is done in terms of what you put into the registers and what the expectations are for that. And the handler, what it does, basically it sets the GPIO to output, and it has this is trivial code that just toggles the LED operation. And in a normal world, so in Linux, we can have a kernel module, we just execute the SMC0 operation. So when we do SMC0 instruction, we jump to secure world immediately. So if we put the cafe value into the R0 register, then we would trigger the operation and turn on the LED. So this is a trivial example on how you can have the non-secure word communicating with the secure word and asking for, in this case, the LED to be turned on and off. But of course, you can have more elaborate functionality, such as asking for encryption, decryption, and so on. So on Android phones, for instance, the keyring is implemented in TrustZone, for instance. So the normal word asks for the secure word to do cryptographic operations. Now, so I mentioned a lot for the file manager functionality and so on, and we propose this hardware as a platform, of course, which is as open as it can get. It runs Linux, standard Linux, so you can just use it as, as a normal device. I have it here plugged to my laptop, so as you can see, I can just SSH to it. So wait, if I type the right password. So here I'm just, connected to my USB device. This is an Arch Linux setup. We can see we have 0.5 gig of RAM available, and we can even, so we can run whatever application we want to. We can even have a complete desktop session running on it. So I just executed VNC server, and here I can just log in and have my, my FSE session, which is running on my USB device. So this is just one example of the power of such a device. But what we've done an application which is called Interlock, and we just made the first non-beta release today of this application. It's available now on GitHub. And this is an open source file encryption frontend, which is developed for the USB Armory, but of course is not limited to execution to the USB Armory. You can run it on a Raspberry Pi or whatever server that you want, any Linux-based device. And the idea is to provide a web-accessible file manager, which is directly tied to the Linux Unified Key System encrypted partition, and that can also perform additional symmetric and asymmetric encryption on the stored files. So the idea is to have something which provides easy access to encryption capabilities. So I'm going to demo that. If the demo gods have been kind to us, now I'm going to demo this application. So I'm going to start it here, and I'm going to connect to it. So the first thing that we see when I connect to it is that it validates my client certificate. So this application, if you want to, you can set it up so that it will demand a valid certificates from your own CA to actually connect to it. So if you don't have a valid certificate in the browser, then it's never going to present you with anything, and it's never going to unlock the partitions. This is one feature that we have. Of course, this is a SSL protected connection. So the authentication credentials of these applications are directly tied to the encrypted partition. So the username, so to speak, is the volume name of the encrypted partition, and the password is one of the many passwords that you can have for that storage. And the reason why you can have more than one password is that these passwords can be disposable. So if you connect the device to a computer which you don't trust particularly and you worry about keyloggers there, you can make sure that the password, as soon as it's used, it's gone. So it can never be used again for unlocking this specific partition. If this is the last password available in your system, then your encrypted partition, you will not be able to unlock it ever again. So now I'm not going to dispose my password, and I'm going to log in. As soon as I log in, the encrypted partition gets unlocked. So everything that you see here, this is kind of a Google Drive kind of interface where you have a file manager, and all of these files here are stored on the encrypted partition. And uploading files is as easy as just taking a file and drag and drop the file here. So now the file, you can also drag and drop directories. So now the file has been uploaded here. And once it's uploaded, so we have file managing features such as copy, move on the encrypted storage, delete, rename, and so on, but we can also encrypt it. And we can either encrypt symmetrically, so with a symmetric password. So here we have the encrypted file. Or we can also encrypt it with your PGP keys. So here I have 2 PGP keys, and I can just decide to encrypt the file with PGP. I can either generate encryption keys on the device, or I can import existing keys on the device. And of course, you can also decrypt, sign, and verify. You can also make zip files if you want, and you can, of course, download the files. And you can take advantage of the fact that we have a file manager that also allows multiple selection, such as that, so I can delete the file. So the idea is that if you want to share a file, you can unlock your encrypted partition, you can have it encrypted on the USB Armory itself with your private keys, which are on the USB Armory, and then you can download the encrypted file and share it. And this API does not allow to retrieve private key materials. So once you upload a private key, once you generate a private key, you can never get it out of the system through the API. You would have to use other means such as SSH with other password and so on. Here you can add and remove all of the passwords that you want for the Linux Unified Key System. There's also a patch called nuke looks, where you can have a password which triggers destruction of the encrypted partition. So rather than having your last password as the one that if it's disposed, everything is unusable, you can have one specific fail-safe password that when used, the encrypted partition will be destroyed. And also one of the features that we implemented and we're announcing today, we also enable text secure and signal functionality inside this tool. So right now, so we see here we have the audit logs of everything that's going on. They're also saved here on a file, which we can also view, by the way, from this interface. So right now, this instance of Interlock is connected to a registered phone number, which has been registered with this application using the text secure signal protocol. So we have a directory with all the contacts here. And if I ask Daniele to send me a chat message from its own USB Armory, also running Interlock, also registered to a phone number. So if network connectivity works, let's see. So here we see the notification that I received a message from his mobile phone number. So his mobile phone number is actually registered to the Interlock instance, which is running on his laptop. And here I see that I received a message from unknown because I don't have it in my address book. I can also rename this contact, and then I can know that this is Daniele. Sorry, maybe without that suffix there. And I can open a chat. Is anybody out there? Hello world. And then I can send messages. And this works not only with other Interlock instances, of course, but with any text secure and signal user. So you can upload your contacts here, and you can send messages to any mobile phone number that is registered on text secure and signal. So you can receive messages and send messages, and you can also send and receive attachments. So now Daniele is going to send a file to me. So he has Interlock instance here, and it just trigger a send attachment action. So here we see in the log that an attachment was saved from Daniele. And if we see in the chat, we see that I got a message. Okay, I received this attachment. So if I go into the attachment section, there's a file here. So I know that it's going to be an image. So the text secure protocol doesn't give you right now, this library doesn't give you the content type, but we're going to fix that soon. So I need to know what it is. And then I can download the file. Oh, and by the way, these are files that are handled by the file manager. So of course, all of the actions that I show you, you can also do on contacts and attachment. You can encrypt, you can decrypt, you can compress them, you can download, you can sign them, you can do all the file manager functionality you can also do on these attachments. So I can download this attachment, and then I can open it, and it's a picture of a lovely cat. This is my cat Nami, first time on Black Hat. So we just shared a file to each other. So Interlock not only allows you to do encryption capabilities, but by plugging into the text secure and signal infrastructure, we can also easily share files with, or chat with other users. Can you send me one more attachment? Yeah, so now I got another one, and this is a text file. So I can also view the text file here. And all of this is being executed on the USB Armory. There is no, this is just, the browser is just acting as a client to all of this. All the data remains on the USB Armory, all the communication is done by the USB Armory, all the text secure keys are stored on the USB Armory on the encrypted partition. And as soon as I log out, So I can also power off the device, but as soon as I log out, the encryptor partition gets locked and all the data is safely stored there. And of course, you can have different volumes if you want. You can also have a decoy volume. If somebody asks you to unlock it, you can present, picture of kittens, and then your porn is safe into another encrypted partition folder. So you can do something like that. So this application is completely open source. It's written in Go because that provides us a static binary that we can easily deploy on such a device. There's a clear separation between the presentation layer and the server layer. So all of the JavaScript, HTML, all runs client-side, and the server is a JSON server with a clearly defined API for all operations. And you can take a look at the API and see how the protocol is implemented. We try to be as minimal and as efficient as possible. And we also have a minimum amount of external dependencies. So all of the features that you've seen except text secure integration are done natively by the application without using any external library, just standard Go library. And the text secure integration uses a single external library that we use. We support OpenPGP. So we don't pipe to GPG binary. This is all natively done in Go. We have symmetric AES ciphers. We also have security tokens. I haven't shown this, but you can also have your TOTP, your one-time token here. We're talking about the Google Authenticator tokens, for instance. So this is my GitHub token. I can refresh and I can have my token here. So instead of having the Google Authenticator app, you can have a backup here. So you can also have one-time tokens or all stored and backed up in there, and you can also use them. And we have now text secure and signal support. And yes, if you look at the API, it's very easy. We have JSON requests from the client for logging in and logging out. And all of these requests are tied to LUKS commands for either opening, mounting, or unlocking the encrypted partition and downloading the files. It's all open source. It's all been released today with the text secure signal integration. And we hope to build up more functionality into this device so that we can have easy sharing of files using an infrastructure which we believe to be secure, such as the text secure signal framework, and to have direct communication between these two devices or other clients that use this protocol, such as your mobile phone and so on. So I think we have a few times for questions. I thank you very much for your attention and for your interest. Any questions? There, yes? Yes, this is available. If you go on our website, you will find there are a few resellers, and everything is also open source, so you can also see the design. If you need to build a certain number of devices, you can also make them on your own. Just give the files to a manufacturer. But yes, this is available, and also the host adapter. We also have an enclosure for it. Any other questions? Yes? Yes? Issues with the heat? Not so far. So the temperature is under control. We compile kernels all the time on it, and we haven't had issues or failures so far. So we tested, of course, before manufacturing, and yes, we have no issues so far. And there are things that we can do. We set the CPU frequency on demand, so the frequencies of the sock is only set to maximum when it's actually required, and otherwise it's blocked down. If you disconnect it, it's just like plugging the plug on a normal Linux server. You will start it up and it will recover the file system and so on. There's nothing peculiar to it. So you have the micro SD file system and it will be recovery output, just like any normal server. In my Armory, I've set it up in a way that when the power is off, when the shutdown procedure is complete, the LED turns on. So I turn it on a boot, it turns off when the boot is completed, and then it turns on again a power off so that I can have visual feedback that the shutdown procedure is completed. But it's anyway really fast. If you shut it down, it takes 2 seconds to shut down. Any other question? Yes? The boot? So U-boot is plain text, but it can be signed. with encryption keys that you can fuse on the system on a chip. So you can fuse up to 4 signature keys, and then you can sign new boots, and that single device will only boot things that are signed. If you lose your private keys and you're not able to sign anything, then this is a brick that you can just throw away. So it's also an interesting feature for nuking. Instead of nuking the encrypted partition, if you want, you can also fuse random signing keys and then make also the hardware device unusable if you want to, but yes. We ship it without keys. We plan in the future to have an option that when you order it, you give us your public key hash and we fuse it for you so that you know that in transit, the device can only boot your code. So that's one thing, but we gotta be careful with that because, you know, there's some customer support issues there. Some people might not have generated the key properly, or they might lose the key. So it's something that is only for advanced users, but of course it's quite possible. Yes?
For the interlock application, that's your web application for interfacing with this USB device. Yes. Are you doing anything about the browser cache to make sure that you're not leaking all your encrypted information that you're pulling out of the device?
Mm-hmm. So there's a set of headers that I think we set. It certainly must be improved, and it will be improved. But I think we're requiring the browser not to cache anything from it.
Okay.
Daniele, correct me if I'm wrong. I think we set a header for that, yes. And we have some cross-site request forgery protection as well. I saw recently a very nice article about additional Go modules that allow more protection. I kind of don't want to use external dependencies, but I might pull in that code and add more protections. And if you have some pull requests, of course, they're always welcome. Any other questions?
Yes, sir. You're doing a lot of crypto work there. What is your random bit source?
Right. So we do not reinvent crypto. So we use the standard Go library, which I would say it had issues in the very early stages, but now it's getting more and more audited, and they're also going as far as implementing side channel protection and so on. And for the randomness source, we pipe directly to the Golang crypto library, which we think provides an adequate support for that, and which it also uses Linux kernel encryption features. We also have, on this specific system on a chip, there's a true random number generator in hardware, and there's a driver for that, which works. We haven't tested it yet specifically, but you can also use that. There are also several cryptographic coprocessors on the system on a chip. However, some people, they prefer to have encryption done in software that they can control rather than the encryption coprocessor. So far we don't leverage on them, but using them is just a matter of enabling the right options in the Linux kernel. So all of the drivers or most of the drivers are there. So that's a layer which is above our interlock software.
One other question: are the specifications for the TRBG opened? Is it available from the manufacturer?
Yes, the data sheets tells you the registers and all the API that you need to use for the random number generator, and the driver is open source and provides you insight in how it works. Freescale doesn't give you the exact insight on how internally the random number generator works, but I don't think you will find any manufacturer that does that. But at least you have the option of either feeding from other sources or using conversional Linux kernel random number generation.
Thank you.
Thank you. Any other questions? No? Okay. Thank you again. And if you want to see the device,